Hi, in this video we'll talk about permutations, but before that we must make ourselves familiar with a very important notation, and that is the n factorial. In one of the problems of our previous video we came up with the result 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. This is actually a result of the form n multiplied by n minus 1, and we keep multiplying until we reach 1. This result is so common in combinatorics that it actually has its own symbol, which is n followed by an exclamation mark. Okay, so the n factorial is the product of all the integers from n all the way down to 1. Now, as you can imagine, the n factorial can be an extremely large number. One may not make an attempt to calculate this number immediately, as in many cases it is a part of a bigger formula. We take as an example 10 factorial divided by 8 factorial. Calculating the numerator and the denominator separately would be a tedious process. On the other hand, if we expand the factorials, we see that many of the terms eventually cancel out, so that the final answer would be 90. We may also consider the n factorial as the product of a sequence of numbers. Let's take, for example, the sequence 0, 2, 6, 12, and so on, so that we get the second term of the sequence by adding 2 to the first. And then we add 4. Then we add 6, and so on, so that our sequence has the general formula n squared minus n, which corresponds to the general term, also known as a with n as an index. So to get the first term of the sequence, we set n to be equal to 1, and we get 0. For n equal to 2, we get 2, and so on. In the case of n factorial, our sequence has a much simpler general formula, and that is a with n as an index equals n. So the first term is 1. The second term is 2, and so on. So all we have to do now is to take the product of our sequence. Fancy notation for that is the letter capital Pi. This notation is used to describe the product of a sequence of numbers. On the right side of the letter, we write the general term of the sequence. The lower index represents the substitution that we make on n in order to take the first element of the sequence. To take the other elements of the sequence, we substitute n by n plus 1, n plus 2, and so on, until we reach the upper index k that will represent the last term of the sequence. We understand this concept better with a few examples. Okay? So let's say that we want to calculate the product of n minus 1 divided by n squared. N starts at 1 and ends at 3. Okay? So the general formula of our sequence is n minus 1 divided by n squared. So to get the first term, we substitute n to be equal to 1, and we get 0. for n equal to 2, we get 1 divided by 4. And to get the last term, we set n to be equal to 3, and we get 1 divided by, 2 divided by 9. So our product is equal to 0 multiplied by 1 divided by 4 multiplied by 2 divided by 9, which is obviously 0. Okay, so let's make another example. Let's say that we want to calculate the product of n squared. N starts at 3 and ends at 5. Now we can calculate this much quicker. We substitute n and we set it to be equal to 3, and we get 9 multiplied by 16 multiplied by 25. Okay, so now we can construct the general product formula for n factorial, and now we know that k factorial equals to the product of n begins at 1 and ends at k. We can now construct the general formula that finds the permutations of n objects taken k at a time. Of course, in order for this formula to make sense, k must be lower or equal to n. So the formula for the total amount of permutations of n objects taken k at a time is equal to n multiplied by n minus 1, and we keep multiplying until we reach n minus k plus 1. So let's calculate, for example, the total amount of permutations of 10 objects taken 5 at a time. According to our formula, this is equal to 10 multiplied by 9, and we keep multiplying until we reach 10 minus 5 plus 1. That is actually equal to 10 multiplied by 9 multiplied by 8 multiplied by 7 multiplied by 6. And if you remember, that was the answer for the question 4 in the previous video. What we wanted to find was the total amount of pentapeptides that can be constructed using 10 possible amino acids with no repetitions. So what we actually did was to find all the permutations of those 10 amino acids taken 5 at a time. As you may imagine, from now on we will be able to solve problems in a more elegant way. At this point of the video, we should mention that there exists another closed formula for the permutations of n objects taken k at a time, and that is equal to n factorial divided by n minus k factorial. Personally, I prefer this formula better, and for a very good reason. If we substitute in this formula k to be equal to n, we see that the permutations of n objects taken n at a time is equal to n factorial divided by 0 factorial. Well, we have not yet defined 0 factorial, but we have already learned that the permutations of n objects taken n at a time is equal to n factorial. So these two have to be equal, and consistency forces 0 factorial to be equal to 1. So to sum up, today we learned lots of things. We talked about the n factorial, which is the amount of permutations of n objects taken n at a time. We constructed the general formula for the permutations of n objects taken k at a time, and that is equal to n factorial divided by n minus k factorial. And last but not least, we saw that 0 factorial is equal to 1. Okay, so that's it for today. And in the next video, we will talk about combinations. Have a good day.